Great. So it's a pleasure to have Ignazio Scimemi here, and he will talk about Hadron structures and TMD factorization. Please, Ignazio.
Okay, thanks a lot, Sibyl. And it's a pleasure to me to give a seminar in Santiago. I think there are a lot of points of connection between the research we are doing, at least with my group here in Madrid, and what is doing several people in Santiago are doing. And I remember a few years ago, Miguel Garcia Echevarria came there to give a talk, and many years have passed, so I think it was time to give an update of all these research that we are doing. So the subject of my work is about TMD. I will try to give some introduction to this. What happens? It goes slowly. Introduction to this, and oh, no, stop. Okay. And there will be a technical part, probably the central part of this seminar, but probably the beginning and the last part will be probably less technical, and also people which are not really involved in this kind of research, I hope they will appreciate this. So TMDs are object hadronic made out of operators, of quarks, and several matrix elements, which enter in several problems. One of the issues which is studied with the TMD is the origin of nuclear spin, and also the spatial structure of the nuclei. But one can extend and introduce TMD also in observables, where one studies this extreme QCD and beyond the standard model. Basically, one has to construct operators and then observe these operators in nuclear matter. And this goes a bit slowly. Okay, I have put here some of the work which have been done. Actually, I have not included 2020, but I think it's enough. And see, the field had a revival basically 7-8 years ago, when the factorization theorem for Drell-Yan and the semi-inclusive DIS was developed. And my group was one of the groups which was working on this together with Collins and Matthias Neubert, other groups in the world. At the end of the day, after some years of study, we agreed on the formulation of this factorization theorem. And starting from this, the phenomenological studies have started, so that I will try to resume all this development, starting from this factorization of the cross-section for Drell-Yan and the semi-inclusive DIS. I will talk about also the coding of which has been necessary to include this development. And finally, I will speak about the comparison with the data, statistics, and extraction of this TMD. So these are the processes which are analyzed and which we consider interesting. Basically, it's this series stands for semi-inclusive deep inelastic scattering. At the beginning is a normal siDIS with a lepton which collides against the hadron, produces leptons and the final hadron, and then there are remnants. Similarly, for Drell-Yan processes, we consider these as processes where the two hadrons collide, you produce two leptons plus remnants. There is several things which are in common with these processes. First of all, the structure, okay, the main things are these things which are in the lens. Say, the bulk of this cross-section are built out lepton tensor and hadronic tensor. Lepton tensor is this L mu nu, hadronic tensor is W mu nu. The lepton tensor is different, of course, in the two experiments, but the hadronic tensor is actually very similar. So actually, the same TMD occur in a semi-inclusive DIS and in deep inelastic scattering. Drell-Yan. In Drell-Yan, of course, we have two initial TMD corresponding to the two hadronic states that we have. And in semi-inclusive DIS, we have one initial TMD called TMD PDF and a final TMD, which is called TMD fragmentation function. Now, just to make a history bit of this, of how this factorization typically work, I've prepared this slide just, for things that probably most of you know. So Drell-Yan and deep elastic scattering are processes which are known since 50 years, basically, which have been used to prove the partonic structure of nuclei and so on and so forth. There is a way in which these processes are analyzed, which allows to introduce what are called the Parton distribution function. Basically, at the base of this, there is an error concept, which is the concept of operator product expansion. And this works in this way. Basically, we have states which are at very high energy, this Q, and interactions or states which are at very low energies. And the two energies are very separate. Now, one can expand in powers of small momentum over hard momentum, and the result are Wilson coefficient and operators. Now, Wilson coefficients are calculated perturbatively. Operators at the end need a perturbative calculation. And this division introduces a factorization scale, which is called mu, the usual renormalization scale for these operators. So this is a standard vision, and this is what is used, for instance, in the factorization of the cross-section, which depends on the center of mass energy. And basically, this factorization is calculated with some hard process, which is given here by H, times this PDF, the Parton distribution functions, which give the probability to find quarks or gluons, basically inside hadrons. Now, the result of this factorization involves two important concept. First of all, that we can distinguish a quark which belongs to a hadron with respect to quark which belongs to other hadrons. So the quark states, I say here, are totally disentangled. So we can assign a quark to a hadron, a quark to another hadron, and the QCD does not spoil this entanglement, this stuff. The other important concept is that all the non-perturbative QCD information is included in these Parton distribution functions. So if one has an estimate of these Parton distribution functions, either extracting them from experiment or with the non-perturbative methods, one has solved this problem. Of course, this factorization is limited to this kind of factorization, to this kind of cross-section. So one can ask what happens if one considers more differential processes. Do these structures keep the same? The answer is no. Okay, but on the other side, this is always a good approximation. And most of Monte Carlo codes that are used also at LHC are formulated in such a way that only Parton distribution functions are present as the source of non-perturbative QCD corrections. Why the answer is no? The answer is no. Let me consider here an example, and this is differential cross-section for, say, Drell-Yan. So instead of having d sigma over dq squared, I put the transverse momentum of the boson which mediate the same process. And here I put also rapidity. Now, because I have a transverse momentum, I can think to analyze it with a Fourier analysis. It's advantageous, but not necessary. One can do even without. But let me introduce it. So we have this B, which is the conjugate of this transverse momentum of the boson. And then one would hope that the whole process would be analyzed in terms of some hard factor, and we have some distribution which now depend on the transverse momentum, here represented by its Fourier conjugate and a renormalization scale. Well, one can give an operator definition of these, making a calculation, but one observes, even at one loop, this is actually a calculation that I like to make to every student which comes to our group, to realize that there are divergences which are not regulated by naive dimensional regularization, but need an extra regulator. Here we used a regulator that we invented, it's called a delta regulator, which corresponds basically to taking the I epsilon, which appears in propagator, to I delta in the propagator, which comes from some collinear interactions. Now, these divergences cannot be regulated with dimensional regularization, which means that their origin is not the standard one as for UV and infrared singularities. Actually, these are called rapid divergences. We will call it rapid divergences. And the fact that we have these rapid divergences means that we cannot separate basically hadronic states. So all the hadronic states which appear in this form seem to be entangled. So it seems that this separation in distribution, each one is related to a hadron, is not achievable in this kind of differential cross-section. And this was something which was observed by Colin Stopper and Sterman in the 80s. It's not something particularly new. However, the point is that if you perform a calculation this way, we have actually forgotten something. And what we have forgotten is what we used to call this soft factor. And actually, now this picture wants to show that there are it's possible actually to define two sectors, one, for instance, for initial state or for final state. But there is a connection which actually corresponds to a very well-defined matrix element, and this is this red stone, and this is what is provided by this soft factor. So there are some points which I will develop in the next slides. First of all, both initial and final state have these rapid divergences, but also the soft factor have these rapid divergences. However, all cancel when we put everything together. And we can redistribute, if you like, the divergences between the soft factor and the initial and final state, so that finally we can define these TMDs. In practice, perhaps not so in practice, but let's say the picture is this one which is in this plot. It's complicated, but let me highlight it a bit. Basically, in this picture, I show light cone direction, which are pointed as plus and minus. So in processes like semi-inclusive VAS in the bright flame or Drell-Yan, we have the hadrons which are back to back. So for one hadron, we have that most of the momentum is in one light cone direction, and most of the other momentum is in the other light cone direction. Now, if you want to separate the hadronic states, we have to introduce some cut in the rapidity, which are these Yn. And however, in this region between the cuts that we put, we have these soft factors, these soft interactions which appear. Once we introduce this soft factor, then this arbitrary rapidity cut that we have put can be removed, and this is removed basically to the following these arrows. So in formulas, this works in this way. We have the currents, the hadronic currents, which are entering this in the cross section, and we say that this goes into a hard factor, which should be estimated, and then the collinear sectors, which are these phi and deltas, one for initial and one for final state, and the soft factor, which appears to be here. Now, all these phi, delta, S have an operator definition. All of them have rapidity divergences, and it's only the product of them which is free of rapidity divergences in principle. Okay, this is the story. Apart from the factorization, there are corrections to the factorization which are provided here by this white term, which I will not really discuss in this seminar. So what is this soft factor? Actually, this soft factor is a bunch of Wilson lines that goes to minus infinity to plus infinity, and are displaced. Actually, we have Wilson lines on one axis, and there are ones which are displaced at a distance, at the transverse distance. Okay, and then all these can be expressed as exponential of these fields. Why do we have rapid divergences? Basically, this matrix element has an invariance. Basically, say if we multiply the light momenta by one factor and the momenta in the opposite light cone direction by the inverse of the same factor, this soft factor does not change. However, there is something which appears from the calculation that can be proved looking at the singularities that appears, is that the rapidity divergences just produce linear, they are always linear in the rapidity regulator, okay, that we have. Basically, we have, this allows, because say, if you have a single log to the power 1, actually this can always be expressed as a sum of two logs, an ambiguity factor. And this allows basically to express this soft function as a product of two soft functions, which are actually the same as the one before, but where the argument of the rapidity regulator are rearranged. So we have one soft factor now, which just depends on the rapidity regulator of one sector, and one soft factor, which depends on the rapidity regulator on the other sector. And the picture is like this. Basically, we have some overlap with this. Okay, let me, oh, sorry. So we have, okay, this hard sector, then we have this D is the fragmentation, F is, F is the PDF, and this dashed blue line is how this cross-section is actually separated in several parts. So we see that the collinear pieces take some of the soft function which appear here. Now, if one performs this separation, one discovers that there are two scales which has to be taken into account. The mu scale, which is the usual renormalization scale, but we have also this zeta scale, which is the scale related to this division of the soft factor, basically. And actually, this D, which appears here, one observes corresponds, one finds that corresponds to the anomalous dimension of what we'll call the soft function, basically. So there are two kind of logs which should be resummed: the logs of mu and the logs of zeta. If one makes this division, which appears here, and reabsorb this square root of the soft function in the collinear pieces, one actually finds a cross-section factorized into two objects, which are now the TMDs. Here I have not put the scales, but actually they depend now on two scales, this mu and D. And each one of these two objects now is free of rapidity divergences. So it can be, so the two scales can be renormalized. Okay, so this is the final formula for the factorization that we have. So the picture of Collins-Soper-Sterman of the 80s is updated, basically. We have now this TMD, but the price that we have to pay, and that was not noted or not, say, understood up to the end in the 80s, was the appearance of these new scales that has to be resummed. Actually, something was understood about this, but I think it was just a problem of expressing these some more strongly, more explicitly than with respect to the 80s. Now, the fact that we have now this distribution poses new issues. Say, now we have these entangles, say the partons belonging to each hadron, and this is good. But these new functions are not the PDFs. Okay, so there are some new physics, well, new physics in the sense extra non-perturbative correction with respect to the PDF, which can still be encoded in some kind of function. Okay, now, if you want to be operative with this, what we should we do? We should make a perturbative calculation in order to understand the evolution of all these objects, establish phenomenologically the validity of this factorization theorem, and extract this new function. And included in all these, we have to understand if this double evolution, double scale problem that we have can be managed in some way which is more effective than others. So fixing these evolution scales in such a way that we can profit of this formula at best. I have to say that since we formulated this in some years ago, many calculations have been done, and actually for unpolarized TMDs, which is the case interesting, for instance, for LHC, now things are basically known at 3 loops. Actually, we have also the Kasparov dimension at 4 loops. So that now we are starting to make actually all fits with 3n here in the perturbative part. The issue of the optimal definition of TMD is actually something that is original to our work. Now, once this is fixed, there have been a lot of development, in this, a lot of, say, revision of all things, in the sense that what happens when we consider polarized targets, and how are the angular distribution sensitive to the polarization of quarks inside the hadrons. This gives place to a lot of functions which are in this table here, which with funny names, which are reported here. So we have them polarized, Sievers, Elastic, blah, blah, blah. Okay, not all these functions appear at a leading twist. Some appear at a twist 3. The functions which are in pink boxes actually change sign between Drell-Yan and siDIS because of the orientation of Wilson lines. One can invent a function with the gluons, which are in the other table, and also for fragmentation function. And there is also the possibility, which is studied now by several groups, particularly the Kang group in Caltech, but also we also did something of using jets in order to study these TMD. So the field is really strongly developing in this sense. Now, let's see how we can proceed, at least for the polarized case, but also for the rest, in a systematic way to the extraction of these TMDs from experiment. There are several things which needs to be taken into account. First of all, okay, we started from the factorization formula that we had before, and we had to include this evolution. Basically, we go from a hard scale Q to the scale where these TMD are defined. And we have some evolution kernels, and actually we can factor out this evolution kernel, which is the R here, and end up with a TMD which are scale independent, or they just depend on the initial scale where they are evaluated. This is something which is usual, for example, both for PDF, but in every kind of physics. When you have several scales present, you have a scale where you fix your non-perturbative matrix element and then all the evolution factor. This is basically done in the same way. But the problem has its curiosity because of this double scale stuff. Then we go to data. They are all data from Tevatron, and new data actually also the 13 TV now in CMS and LHCb. And then we go to some statistical treatment of this data. I will start with this second line here to tell you some details about this. Okay, this slide, the formula is complicated, but not so much. This is a typical structure which appears, for instance, in Drell-Yan. We have a factor which include lepton tensor cuts, which are done in LHC, electroweak coefficient and hard coefficient, which are have systematically been calculated at a higher loops, and then we have the product of TMD. Okay, now for each TMD, at one set of the 2 scales, we have an evolution factor and this initial TMD. And for the evolution factor, we have basically the Collins super kernel. Now, the Collins superkernel is made out of the anomalous dimension and this function D. Actually, usually this D is called the Collins superkernel, and includes also a non-perturbative part. Okay. And this is up to now. Now, there is another factor which make the PDF enter the game again. And the point is that if this B goes to 0, so if the transverse momentum goes to infinity, one can make another operator product expansion and re-expand the TMD in terms of Wilson coefficient again and PDF, and some new structure which appears. This for which we have really no clue at the moment, but which corrects the PDF behavior. Again, every time we make an operator product expansion, a renormalization scale appears. So we have, you see, another scale, another mu which appears. So I will call this the mu OP. It's the mu of the matching of the TMD onto the PDF, to distinguish it from the mu, the pure renormalization scale, which appear in the factorization of the cross section. Okay, and the zeta, which is related to the rapidity evolution, to the rapidity stuff. Okay, so we have, so the normalization group structure is complicated. It's not as standard as usual. So let me spend, given this, some minutes to describe how the evolution really works. We have for these TMDs two evolution equations, one for the mu scale and one for the zeta scale. So forget for the moment is the mu OP scale, the third scale. Now, one goes with what is called the standard anomalous dimension, and the other is the solid Collins superkernel, this function D, which is extracted from the sub-function that I had before. These differential equations are not independent. Say if we can derive the upper equation with respect to z, the lower equation with respect to mu square, and of course the result have to be the same. And actually this introduces a link between this anomalous dimension and the Collins superkernel. Basically, the derivative with respect to zeta of this anomalous dimension is the cusp anomalous dimension with the sign, and we had a sign because we had a sign here, and the inverse is also true. Okay, so there is these differential equations are coupled in some way. Now this is true always, is a non-perturbative statement, and it has also a consequence. Basically, if this is true, so one can set a couple of initial scales and a couple of final scales, and join going from one point in this plane to the other point with following a path, and the result is independent of the path. Okay, and this is good because I mean this is actually what we want. In principle, we do not want that our result depends on the path that we choose. However, this is not true in practice. It is not true in practice because our knowledge of the perturbation series is of this anomalous dimension is partial. Basically, we have just a few loops. Okay, we have 3 loops, which is an important result, but it's not it is not infinite in a sense. So, what is the outcome of having a truncated perturbation series? It means that this path independence is not true anymore. Actually, our evolution kernel depends on the path. So, choosing a path in this upper rectangle or in the lower rectangle introduces a difference, and this is also different from from going through the diagonal. Okay. Now, if one looked at what was done in the history in the standard programs, I don't know, but also programs which are used up to now, like DYNLO, ResBos, and so on, this is the only path which is considered. They never consider this, they never consider this, no other alternative. However, this is not the most efficient thing that one can do. And let me show you what we have ideated for this. And I will then introduce this with a notation which is taken from electromagnetism in 2 dimensions. And because of this, it's really somehow evocative, I would say. So let me put the 2 scales, the mu and zeta scale, this is the log of these scales, in one vector, which is called nu, and consider the gradient with respect to this vector and the curl of this vector. Now, the anomalous dimension, let me put it in another vector, which behaves like an electric field. Okay, we have this gamma f and d. Now, one can take the gradient, this gradient here, apply it to a TMD, and observe that this is actually equal to the electric field vector times the same TMD. The integrability condition means that actually the curl of this electric field is equal to 0. But if this happens, then electric field is actually the gradient of a potential. Okay. Now, if this is also, no, sorry, let me go here. If this is true, what is this potential? Actually, the logarithm of our evolutional kernel is actually the difference of the potential between 2 points. Okay. And the expression of this potential is actually the usual evolution kernel that we have, that I have shown before. Basically, so this means that I am making an evolution only if I go from one point to another point in this new space, which have a different value of this potential. However, this means that in this plane of zeta and mu, there are what we call equal potential lines, which are these gray lines, which are depicted here. Actually, the spectrum of these lines change depending on the values of B, but the picture is always the same. We have these equipotential lines, which are these gray lines. Okay, and if we have 2 points, we stand on the same line, basically there is no evolution. And these fourth line, the one with the arrow, are the one which are, we say, it's the gradient of U, basically, of our potential. One finds also that the structure of lines had a saddle point, which is this point here, which is the point basically which has no evolution at all, for which our function d is equal to 0 and also gamma is equal to 0. And this point actually depends on B. So for every value of B, we can find one and unique saddle point. I have not depicted here the Landau pole, which is on the left side of this figure. However, okay. And now one can think, suppose that we define our initial point of the TMD on this saddle point. Now, this initial point is basically very stable because there is it cannot change. It's a uniquely, say we have a unique non-perturbative definition of this saddle point. So this removes one of the biggest uncertainties that we have when we estimate the TMD. So what is the initial scale, the optimal initial scale of this TMD? We have an answer for this, and the optimal point is the one for which all the anomalous dimensions of the TMD are 0. And we know this point exists, and we have a way to estimate also non-perturbatively this point. And this is important. Now, the consequence of this, let me repeat a bit, is that you see I have depicted here TMD as different on different lines. So if I cross the lines, the equipotential lines, I have an evolution. If I do not cross equipotential lines, I have no evolution. And now, this is how this double evolution actually works. Okay, this is again restating the same. So TMD on defined on sets of conditions which are the same equipotential lines are the same, and we have just evolution going from all course. So we have so if you like, we can compare now what with respect to was done by Collins in 81 or in 2011. So the standard way to understand this evolution kernel is to put an initial scale, this mu0, and do something like this. Basically, in this plot, in this diagram where I have the zeta and mu plane, I go on one side of this rectangle, then I flip and I go on the other side. And the point where this flip is done is actually this mu0 point. Okay, this is in picture. In the thing that we propose instead is something different. So we reason in this way. Instead of choosing a path, defining some intermediate scale, we change one of these anomalous dimensions such that the path independence is restored. Basically, we change this anomalous dimension with a piece which actually can be computed using the beta function, essentially. Okay, so in this way, with this modified anomalous dimension, we can go from the point of the center point to the final point. And the thing that we do is the following, basically. We start with let me do it again. We start from this center point here, say the cross of the red line. We move on an equipotential line, and we go to the point which is closer to the final point that we want, and then we make a small evolution. Okay, we can do another one, or we can do another one here. Basically, or you can think it the other way around. From the point that we want to start to make the evolution, we join the closest say the point with D is equal to 0, basically, and then we can join the center point. Basically, only these vertical lines are interesting for the evolution, not moving on the red lines, because the red lines are equipotential lines. So all this seems perhaps a bit complicated, but it's not complicated when you code it. And this is what we have realized when we coded it with our code, which is Artemide. Now, so the message at this point is that to conclude this part, then I will go probably more to phenomenology, is that when analyzes this differential cross-section, we have two factorization theorem which works depending on the value, the ratio of Qt over Q, or the transverse momentum with respect to the high energy that we have. If they are of the same order, basically everything can be treated in the standard way with some hard interaction and PDF. If this Qt is much smaller than Q, then we go to the TMD regime, and instead of the PDF, we have the TMD, but now we have this problem with double scale. And we know how to treat this problem with double scale actually in a very general way. If you are in the intermediate region, of course, then this is problematic, because then we have a factorization breaking terms from one side and the other, and it's one should discuss which one is better, if going from up down or from down up. Okay, and probably this we do not have an answer at this moment. So let me move more closer to phenomenology. We had these our TMDs, which are written here. Now we can re-expand them in terms of Wilson coefficient and PDF. This happens for PDF fragmentation function. Here reported result at 2 loops, one time also by our group, but then recently also 1 year ago already, this result at 3 loops. And then this function has to be corrected by something else, which corrects the PDF behavior. What do we put here? Actually, we have tested the models that came to our head. We had basically no clue, or almost no clue. So we expected that the behavior at a large B going linear in B, because things in pions in character perturbation theory go in this way. So we expected models which go like Gaussian when B is small and exponential when B is large. And we have found that these models need an X dependence, so they really correct this behavior of PDF, or a Z dependence in the case of fragmentation functions. Okay, and now we go to rewrite the cross section. The red term, which are in the first line, are the one that we had before, probably written in some different notation, and the blue terms are the power corrections which are expected, which we have not included in our fit. Basically, we have no clue of this power correction. We can classify them, but we are not really able to calculate this power correction. But okay, we expect them to be small in our stuff. The convergence that we have is good, I would say. We go up to entry LL. You see, we have in this plot we have plotted here. Okay, the leading order is always very bad, but as soon as we abandon the leading order, I have to say that all things are within really few percent. We are around 1% here in the case of the Z boson production. And of course, the convergence is a bit worse when we lower the energy. Here we are at 25 GeV of square root of S and 80 GeV, but still we are, I would say, within 5% here. And in siDIS, this is extremely low, but we can manage to do things with the precision of less than 10% still. So this is, yeah, with our prescription and so on. So the perturbative convergence that we have is enough to use the current data and to make phenomenology with them. Now, speaking of phenomenology, let's go. What data do we have? We have data from LHC, and we have data from other experiments, which are some of them are old, like this E288, E605. Some of them also Hermes is a DAISY experiment of some years ago. Phoenix, there are some new recent result, a few points, and Compass has published its result a few years ago. There is a big gap between the LHC data which are provided and these low energy data. And we have asked the LHC community to start to be interested in this intermediate region, and things move slowly. Who knows if in 10 years we have data also in this region. But the other good point is that EIC is also moving. So, we hope to fill this gap in energy in the next years somehow. Okay. And then we have started to formulate these questions, our questions on data. So the first question is when all this formalism is valid. This is a recurrent question, and actually our answer is developing. So in the fit that we did in 2017, and then which was confirmed also by other fits, by the Pavia group and our fit of 2019, actually, we studied what the fraction of this Qt over Q, so transverse momentum over boson energy is relevant for our TMD studies. And we found that from the chi-square analysis, basically we should always expect the TMD formalism valid when this ratio is below 0.2. Okay. Why 0.2 and not 0.1 and not 0.4? We don't know yet, but this is a kind of phenomenological figure that data at least seem to suggest. Okay. Now we have to compare in order to fix this figure also with the error of each experiment. We have done it. And actually for Atlas, we took even a stringent range. We go to 0.1, 0.15. Basically, at some point, increasing the experimental precision requires the introduction of terms which correct factorization theorem beyond the one that we have included. And this changes a bit this limit. So for Atlas, it's a bit more restrictive because of this error. Okay, so but this figure have been tested just taking Drell-Yan data, but also including Drell-Yan plus siDIS data. This is the last figure that we have. And then we started to see which how all the ingredient, non-perturbative ingredient of the cross-section appears. First of all, the evolution kernel, which has some non-perturbative piece. So in green are the extraction of our group, and in orange, the one that are the group of Pavia, basically. We don't agree. We don't agree because, say, we agree in the perturbative region, say with B below 1, I would say, because there is the piece which is dominated by perturbative, but then the prescription of the two groups are different, so this gives a different result for this non-perturbative part of the evolution kernel. So, however, so there is a different parametrization of the non-perturbative stuff. So what can put an agreement with to us if we what can improve this agreement? Certainly new data, but also lattice. Lattice has started to calculate this evolution kernel. There are several groups in the world. One, I would say the Chinese Chinese American, I would say the MIT group, and also the Regensburg group. And I think that this year, there will be further many more results about this evolution kernel. And they give a result for an interesting range. Basically, I do not have probably the picture here, and but the recent data show that our formulation actually is in better agreement with lattice than the one of Pavia. But say, I would say this is just a qualitative, and say we have to wait for the new result, which probably will appear this year, to establish if one parametrization is better than the others, at least in this respect. However, we have also many interesting results that we have discovered. For instance, we have considered several sets of PDF and how, if the fit depended on the set of PDF that we used. And the answer is yes, depend pretty strongly on the set of PDF. So HERA PDF seems to work much better than the others. Okay, and this was curious. We didn't expect when, at least some years ago, why, say, we thought that the agreement of PDF was such that one could fix all these non-perturbative model in a pretty good way. But this is actually near not the case. Using different PDF, the quality of the fit really changed. So we have some set of parameters, the one of the evolution kernel, which can be fixed pretty well. I would say there's an agreement. Not only, say, in this graph, which I show here, the points above correspond to fit of Drell-Yan, and the 2 points below correspond to the fit of siDIS plus Drell-Yan, which we consider at the moment our final result. So the band corresponds to this fit of siDIS with Drell-Yan, with two different sets of distribution of fragmentation function, I have to say. And say, for the evolution kernel, we have, I would say, an agreement, more or less, okay? But however, for the other parametrization, there is a spread of result in most of the, when looking at most of the sets. So, what's going on? This is actually what we are studying now, and I will not show probably too many things because it's something which I are trying to see. This is curious. So this is an object of our study in this moment. Why the TMD are that we have at the end of the day depends so crucially on the PDF sets. Okay. Now, another thing is the PDF error that we have on the TMD. And in this plot, we compare the scale error, which is this blue band, with the PDF error. And we see that the PDF error is actually dominant with respect to the other one. So also here, what should we do? Refit PDF, or we should make a global fit of PDF and TMD in order to eliminate this error? These are things which I do not have an answer up to now. There is something which confirms all the settings of the fits that we have been doing, and let me explain these plots in this way. So once we build the cross section, our statement is that there is a non-perturbative part related to the evolution kernel and a non-perturbative part relating properly to the TMD. And actually, they have different origin. They should not be correlated. So, of course, when we extract all these quantities from a fit, one can have some correlation. And if the parameterization is good, however, the correlation is small. And this is actually what we observe in this picture on the left. This is our last extraction. We have the two parameters on the top left, which are basically uncorrelated with the rest of the parameter of the fragmentation or of the TMD. There is some correlation between these C0 and lambda 1, but for the rest, I think things go pretty fine. This statement depends a bit on the PDF sets. So this uncorrelation is better for the best PDF and worse for the worst PDF that we have used. And we have to say that if one look at the Pavia group that did another prescription for the implementation of the TMD, actually they have really, everything is correlated with everything. And there is no clear separation between the parameter of the evolution kernel and the rest. So actually observing these details which are predicted from the theory is interesting, and it is affected by the way you implement the TMD sets, the cross section in the code. Here is a bit a resume of the results that we had, same as before. So they have the chi-square, the value of the parameter, which say they change, and of the parameters of the TMD. Basically, they're the same tables that I had before, but perhaps in some bigger form. Okay, probably I can skip these. And another question that we are posed is what happens if we just use LHC results? We have done this analysis. Of course, we are, because LHC results are just at high energy, we are not sensitive to all so the finest details of the TMDs, but we need just to modelize in some simpler way. Basically, we need just one model for the evolution kernel and one parameter to fit the TMD data. So what we find is that we always need, however, some non-perturbative information to describe this data. This non-perturbative information can come from the evolution kernel, can come from the TMD, but the best is that we have both TMD and evolution kernel non-perturbative input. Okay, and this is the result of our study here. Actually, we compare the evolution kernel that we have from our global fit to this kind of modeling of that we use for the just for LHC, and in general there is an agreement. Well, the best agreement is the one where we have a structure with we have non-perturbative inputs both in the evolution kernel and in the TMD. And this is something which is unpublished. I think just a few slides. So we try to give a more quantitative estimate of the sensitivity of TMD at high energy, at LHC. So which beams are actually more sensitive to the TMD. And we varied this boson energy. And we observed basically that all data, so when this QT is below 5 GeV, are sensitive to the TMD independently of the energy of the boson. So this opens the way, our path to use actually more data at LHC, say, using the first bin of every experiment that they have, because the first bin usually take 10 GeV basically, or less, or we can ask them to make, say, first bin of it at 5 GeV and make a plot at several energy. And this part here is always sensitive to these TMDs. And okay, this is something for LHC people. They started, well, to make some analysis some years ago in the LHCb, but then I don't know, they just thought it was not interesting and they forgot probably. So these are our plots for the Z spectrum, basically at CMS and LHCb. And also we have included here data below the Z spectrum and above the Z spectrum, and compared to the. So you see that in general there is the agreement is pretty good, I would say. And here we start to give some prediction for the W's. Now, the problem with the W's is that the flavor structure is a bit different from the Z. So this poses the question if we can we should modify our modeling or the TMD or not. And I think probably yes, we have to modify them. We have to redo things. At least, say for the old data of the W's, we have really no problem, I would say, or much less problem. But for Atlas, they have just 1 point, a couple of points, things are fine. But for CMS, we are a bit off. Basically, sometimes we are off in one. These are numbers with a few points, 3, 4 points for experiment. So if you are off 1 point, basically the chi-square goes goes very high. And these numbers should be taken with a bit of granularity, but I think that there is some space of improvement also when including the data on W's. Okay, this is a final picture of our three-dimensional distributions, how they appear in fragmentation of TMD. Say they are in B space. The horizontal axis are this B parameter. Vertical axis, the obliquous axis is the X, the Yorken variable. And so this picture shows how these transverse momentum are distributed in this space. So I arrive now to my conclusion. I think more or less it's time. We have actually now theoretically, I think, a clear picture of what is happening in this transverse momentum distribution, this differential cross-section of transverse momentum distribution. We have a factorization theorem and also many perturbative calculation for the unpolarized case. Not so. This situation is not so not the same for the polarized case, and much work has to be done for the other cases. Experiments have not looked at this problem probably in the proper way up to now, and we are pushing to do it in the future. Who knows if we are successful or not. But at least we have an electron-ion collider, which is going to be built. And so if I think this is healthier, both for LHC and say, it's good to have at least one experiment, because it can stimulate also another experiment on another side. And the ideal situation is to have more than one experiment looking at these things so that we can compare things. For the PDF, we have found some problems that we are studying now, and we don't know yet if it would be better to do a joint fit of PDF and TMD, or what can we do to solve this problem. So what we are trying now is to see if the problem comes from our modeling of the TMD. So being more flexible in our modelization of the TMD, make the accord with the PDF better. And the answer is probably yes. Things are going to be better, but of course the meaning of our parameter will, the value of these parameters will change a lot, going from one PDF set to another. So in some ways, somehow shifting the problem to another place. There are some TMDs, which are the one given by gluons, which are okay, in theory, they are well developed, very good calculation, but extracting them from experiment is really cumbersome because they involve heavy quarks. And so things get more difficult, so more QCD effects appear. And it's good that several lattice community are starting to calculate all this stuff from scratch. So hopefully in some years, if experiments do not arrive to precise determination of these TMD, at least we can have lattice results and see if things really work as we predicted. Wow, I think it's all for the moment.
Great, thank you, Ignazio, for the great talk. Let's give him a round of applause.
Okay.
If possible.
Yeah.
I have in the chat Nestor and Carlos saying that they had to leave, and sorry, but thank you for the talk. Otherwise, are there any questions? You can unmute yourself normally.
Yeah, well, if I may, I might have one question. Okay, so thanks for the very nice talk. I learned